Victor, I'll transfer the floor to you. Thank you.
Very good. Good afternoon, everyone. Thanks, Gustavo, for the opportunity to share this interesting and I think important topic about helping dairy farmers to improve the sustainability. Before I continue, I should give a shout out to Tadeo. I saw in the attendee list here, he is also part of our group in the webinar today. So he has been critical for the development of this DairyPrint model. He was postdoctoral researcher in my lab until last year. Now he's in Vermont, but I still kept his affiliation with UW Madison. He did all the work while he was here, and we recently submitted a paper, and we hope we will have some published work on this, in addition to the actual DairyPrint model that is already available. And hopefully at the end, we're gonna be able to see live and have a demonstration live of the DairyPrint. Okay, without further ado, let's get into it and what we have done, why we have done, and why we think this is useful. So the first thing I wanna start with is with the root problem. Why we think this is important. We all know greenhouse gases affect global warming. We know there are different sources. We have transportation, we have manufacturing, all they have their own carbon footprint. And the dairy industry also has a carbon footprint. There could be a lot of debate, more or less, how much the dairy industry contributes. I think in the big scheme is not a huge amount compared to others. However, I do think every single industry has a responsibility to decrease the emissions as much as possible. And this is going to come into scrutiny even more as we move forward into the future. So I think everything we can do in that regard is going to be useful from the standpoint of view of the sustainability of the dairy industry. So we want to quantify greenhouse gas emissions from all the significant sources in dairy farms. But this is difficult because, as we know at the moment, it's not possible to measure. Even if it is, nowadays with new devices and technologies, we could potentially do it, but it should be extremely expensive and not practical. So same thing will apply to doing nutrient balances. If we are working on greenhouse gas emissions, I think it's prudent to also think on other nutrients that are being emitted or used on dairy farms. So we should think on a more holistic approach on the environmental standpoint of the dairy industry. So because of that, we rely on mathematical models to have a quantification or estimate of the emissions on dairy farms. However, the important point I think in this slide is these models available nowadays normally are cumbersome and overwhelming to use for the final users. And let me go a little more in detail on that. In order to quantify, if we all agree, we need to use some level of mathematical models. Even these life cycle assessment applications will require some mathematical models. And the models we have out there, which are great, like for example, I have been or become quite familiar with the integrated farm system model, for example. And nowadays, I'm part of a big national group working on the RUFAS model, the ruminant farm system model, that if you haven't heard about it, actually, it's gonna become much more widely disseminated. It is actually in the in the plans to replace the Farm ES in order to do the accounting of the environmental standing of the dairy industry in the near future. Okay, but the point I want to make here is all these great models which are out there require a large number of inputs to populate. Normally, they will require a good level of training or guidance to be able to use these models. And normally, even though many of these have become to fruition as decision support tools, they normally end up to be more research and education oriented, mostly research. They're great for doing a lot of research, but our idea was somehow different in this case specifically. This was our philosophy and still is regarding to this. In this little theoretical graph, we have on the x-axis the level of detail of potential models we can work in any area, in this case more specifically to estimate greenhouse gas emissions and other emissions on dairy farms. And then on the y-axis, we have the probability of adoption, depending on how much level of detail we have in the model. So if you see, if we go to the right on the x-axis, we go more to the theoretical side, and we will be ending up more on the research side and less usability of the model. And on the left side, we will be on the opposite direction, in which we are more trying to do a model that would be on the viewpoint of the practitioner. So we may think the integrated farm system model and RUFAS and other models are more towards the right, and we wanted to put our DairyPrint model more to the left. The point being, we want a model that's still solid scientifically, but very easy to use and directed to the final users, whether it is the farmer, the decision maker, the consultant. A tool that maybe is not the final one, but a tool that can give you good estimates and still allow you to do decisions that could be corroborated later with more complex models, for example. That's the idea. So we thought, as we developed this DairyPrint model, in a model that would be simple, minimalistic, still robust, and scientifically sound. That's very important, and user-friendly, and that will include all the main components of the whole dairy farm system. And this could be addressed our target audience, dairy farmers, nutritionists, consultants, practitioners in general, who can advise or do directly decision-making on the dairy farm. So here it is, a graphical representation of the DairyPrint. Very simple. You see on top the modules. We have, for example, the herd. We need to simulate and have a herd component. We have the barn, the manure, all the crops. Obviously, we have a component that also calculates the economics. And obviously, we need a dashboard or a user interface that has to be as user-friendly as possible. So we encourage the use of this model. Now, I mentioned Tadeo. Tadeo is very proficient in R, and he actually brought with him and learned a lot during this project Shiny, which is like a library, or not exactly a library, but a component that connects with R in order to make these kind of user-friendly applications, as you will be able to experience in the demonstration at the end. Okay, so basically the idea is the user will enter some inputs, the minimum possible. We took quite some time to decide what are the critical inputs that are needed, and we try to keep that at the very minimum level. And then there will be the outputs, and there will be a report, and we can also potentially store this data in a database to further use in the future. And then there will be some improvement opportunity indicators, which will go back to the decision maker or farmer, and then the decision maker would be able to do very quick and direct what if questions and actually find out the results instantaneously. That's the whole idea. Like, for example, here, able to look at the carbon footprint intensity, for example, carbon equivalents per kilogram of milk based on some level of benchmark, how much I'm doing. If I change something, if I change something in the manure management or in my diet, how much that will impact my carbon footprint can be seen in this model in a very easy and direct way. Okay, so everything, it is available, as I said, and we're gonna go there on this website, the website I run, Dairy Management in Wisconsin. By the way, if you haven't been there or not lately, I invite you. There are a number of tools that may be of your interest in different areas of management, all the way from feeding to financial, and this obviously it's in the environmental side of the different tools. Okay, so now let's take a look briefly what the user needs to do to actually have some evaluation of the farm using the DairyPrint model. Okay, everything starts with the herd information. I mean, that's the way we design basically. And so the user only needs to enter a few data points that should be readily available in the head of the decision maker. Actually, I don't think any of these data points would be needed to be retrieved from any management software on the farm. But if they want, it's possible. But I mean, you can see number of cows, total adult cows to enter here. In general, an average of calving interval, cow cooling rate, the body condition score at cooling, etc. Milk yield obviously is important, but all this will be used internally to do a great assessment. Basically, we do a simulation, a Markov chain simulation. So we have the herd population inside. The user doesn't need to worry about that. And we can do that. We need that to do a better assessment of the diets that can be used in different groups of animals and how much emissions will be with respect to that. Same, another thing that needs to be entered here, like, for example, the mature weight of the animals. And then internally, it will be obviously somehow disaggregated, and we will have mature weight for every, we will have weight of every single animal at every stage of their life. Yeah, obviously that's an average, but I think that at the end gives a good representation of what the farm is, and we have been able to not validate the model, but evaluate the model against actual data to make sure it's representing what it says it's doing. Same way for the calf feed management, some important key performance indicators or data points that need to be there. Like, for example, the starter, what level of protein, what level of different percentage of nutrient requirements are in that feed. And on top here, we will have as well milk protein and milk fat percentage that is expected on the milk composition of the milk of the farm. So once this is defined, we will need to do a quick run of the model, this Markov chain model that will give us the population, the herd demographics, and along that, we will have an estimate of the production at different stages of the animals. And along those lines, we will estimate nutrients and greenhouse gas emissions at different levels. Then we can define other aspects of the farm, and this is important, the manure handling and management. And in this case, weather information is important, so location of the farm will make a difference. And here there is a Dropbox menu that allows to select counties in Wisconsin. This is a good point to mention that this tool has been supported by the Dairy Innovation Hub, as you will see at the end. And so it has been envisioned at the beginning for Wisconsin. This could be expanded and scaled up to anywhere. At the moment, the counties that are available here with weather data are from Wisconsin, but the idea and the possibility is to expand to any place in the near future. And then we define the type of facility, the bedding type, the type of management of the manure, including if it is a slurry or another type of management regarding the manure. And if the manure is being stored on a pond, or if it is, for example, used for a biodigester or something like that, as we're gonna see in a moment. And then we also define, this is very important, as we found out, part of the research has been as well to test different scenarios, the emptying time. So if it is emptied only in spring, only in fall, I'm talking about the pond or storage of the manure, that will make a huge difference on the environmental standpoint of the dairy farm. The storage area, obviously, if there is a crop formation, and if it is enclosed or not, the manure, that will make a difference as well, and how the manure is being applied to the fields. Okay, all this, as I said, just to recap all this slide, should be readily available in the mind of whoever is the practitioner or the decision maker, right? So we try, as I said before, and I try to emphasize that point, to make this as simple as possible to be used. And obviously we need diet information, and we decided once again in the phase of making these as user-friendly as possible, to define only one diet for lactating cows, one for dry cows, and another for heifers. Yes, you could argue there may be more lactating cow diets, that's possible, but if that's the case, we will use the average or the weighted average here that will represent all the cows. I mean, it's not rare as well, unfortunately, that many farmers will use, for example, one TMR, one diet for all the lactating cows. Actually, in different projects, we are trying to change that, improve the efficiency of feeding at the herd level by doing more groups. But in this case, the assumption is there is one diet for all lactating cows. And the other point here that's possible with the tool, and that's something to explore more in the future potentially, is there is a nutritional strategy to decrease methane mitigation. This is more specifically referred to some additives like 3-NOP, for example, being used to decrease enteric methane emission. That could be also assessed throughout or using this tool. We all know 3-NOP is not still available in the US or is not allowed to use in the US, but as far as I know, that should be allowed pretty soon. It's in the latest process, as far as I know. It's allowed in Europe, for example. Anyway, so once we run the herd calibration, we will have a little summary, how many lactating cows we have and dry cows we have according to the data we enter, how many heifers we expect to have, how many calves, and actually even gives you what is the herd stability, how many we are producing of female calves and how many we need. So the balance of animals as an additional information, it gives a good idea. The idea here is that the herd remains stable throughout the analysis, which is a very safe and normal assumption, I would say. Now, we will have some performance metrics based on the data being entered, like, for example, how much is the estimated dry matter intake for dry cows, for heifers, for milking cows, Even we calculate how much water is being consumed by different groups of animals, and what's the milk yield. If you remember, at the beginning we asked what's the milk yield as an input, but part of the calibration internally is to come up almost to the same level of milk production, including the herd population. So if you remember the original data, the input was 40 kilos per cow per day, and we ended up with 39.9, which is basically the same number. But this is calculated at the cow level. The number we entered at the beginning was the average of the herd, and we are coming up to the same average using the aggregated production for all the cows on the herd. Okay, so then we will also calculate manure excretion using the latest knowledge in this area. And as I said before, we evaluated this the best we can, and these numbers are really solid actually on what we think they calculated. Same we will do for nutrient excretion, like for example, on top here, nitrogen excretion for different groups of animals, phosphorus and potassium. We also include potassium here, even though we know it's not a heavy concern at the moment, probably among nutrients. Probably would normally concentrate in nitrogen and phosphorus, but those are here. And then we can see actually the excretion by months in lactation for each one of the nutrients here, nitrogen, phosphorus, and potassium, how they change across the lactation. And obviously we aggregate all that. The aggregated numbers are the ones you see on top here. Okay. So now, how about manure and greenhouse gas emissions? As I said, we calculate the total manure production, for example, in this case, 29 tons for a herd of 150 cows, as you saw at the beginning. And we can also calculate, based on the best literature, as I said, the herd methane emissions in tons per year, the barn methane emission, and the storage methane emission as well. So those are very important numbers already, and the ones we're going to look more closely as we do what-if scenarios, right? One thing that's interesting to mention here is these curves. The orange one is the temperature of the location we selected on average throughout the year. The x-axis is the days after January 1st in a year. And how increase, here's the summer on top, and how the methane emission change across the year. You can see it's heavily related to the temperature as it is expected. So this is the daily methane emission on the left side of the barn. If you see the numbers, those are much lower than the numbers on the right, which is methane emissions from the storage. And you can see here, just by looking at the graph, there are 2 points in which the emissions decrease drastically. And those are actually representing the emptying time of the pond. When we actually apply the manure outside, the methane emission will be heavily decreased, and then will start increasing once again. And there will be a heavy relationship once again with the temperature, the environmental temperature out there. So you can see here very graphically what's the impact of emptying more times the manure pond, right? If you empty only one time, there will be a much higher emission than emptying 2 times. And normally we will empty in spring and fall as well, at least. Probably more times, if possible, would also improve that. Here we can see important environmental outcomes as well of ammonia emissions in the graphs. And you can see, once again, temperature is a heavy factor on the emissions, and how it changed across the years of the days of the year. and how it's impacted as well here, the ammonia emission by the emptying time of the pond. So this is emissions from the storage, the pond, and this is emissions from the barn. And we know these emissions are obviously, in the case of methane specifically, are in addition to the enteric methane emission from the cows directly. Because we have this data very well represented, we provide as part of the tool, for example, the temperature across the year for the location selected by the user. And together with that, on top, we have different key performance indicators about manure produced, the total herd methane emissions in tons per year, the barn methane, and the storage methane. And also here below, you have ammonia emissions in different parts or components of the farm. At the end, probably this is the bottom line, the carbon footprint that we are expecting for this farm with these conditions, this diet, this herd population, this manure system, and also these crops. That is also part of the DairyPrint. So in this case, for example, 0.893 carbon equivalent per kilo of milk. It's so if we put one as, in some literature as the benchmark, this is below that, but very close. Obviously, the lower, the better in this case. And we can see this carbon footprint in different breakouts, like in this case, for example, by source of greenhouse gas, how much it comes from the herd. You can see here 44% is the herd, basically, or close to that amount, 0.44 to rephrase, 0.232, about half of that is crop and purchase feeds, and the manure handling is 0.15 in the scheme of that. Much lower here, the barn, 0.013 carbon CO2 equivalent per kilo of milk. On this side, we can see how it break out, for example, the amount of greenhouse gas by farm sources. How much it comes from the herd, 52.6%. This is mostly enteric methane production. How much it comes from the manure storage, and how much it comes from the crop and purchase feeds. And finally here, we can see the carbon dioxide equivalent or CO2 equivalent by type of greenhouse gas. Whether it is methane, 68% is direct methane. About 8.43 was produced as N2O, and carbon dioxide was 23.4%. All this data is very important as we move forward on trying to change some management or doing some management strategies to decrease this and still obviously remain profitable. The other thing that I think it's important to share and show is the nutrient balances, right? This is a very interesting way to display that. These stair bars basically show to the right the entering of the nutrient to the system. In this case, the system is the farm. How much it came of nitrogen, for example, from purchase feeds, how much it came from fertilizers, how much it came in the bedding, how much it came in legumes. It's actually atmospheric nitrogen being captured in the soil. And to the left and in red is how much we are using of that nitrogen in milk, how much is leaving the farm in milk, how much is living in cold animals, barn, manure storage, and leached. This actually is an environmental concern, as we all know. In this case, for example, this amount, 7.34, is being tons per year, is being leached, maybe to groundwater or so, but that's something to keep an eye on, right? How much is the balance? In this case, 6.36, which is unaccounted for, and we need to find out where that nitrogen is being going. How about the phosphorus? We see kind of similar fashion where it comes. Most of it comes from purchase feeds, but also bedding and fertilizers. And most of it is being leaving the farm in the milk, obviously, and in cold animals, as well as we have some losses in the soil, probably runoff of phosphorus, which is, again, an environmental concern we need to look at as we move forward. Okay. So we do have some economic outputs. This is not, I can tell you, it's not very detailed, but I think at this point what we wanted to show is how these economic outputs are related to the environmental changes we're gonna promote or we're gonna try with the model, right? How much is the milk income? We estimate the feed cost according to the diet and the dry matter intake of the animals, and so we can calculate, which in my opinion is the most important economic factor after the net return. Ideal would be to have the calculation of all the costs and benefits, but we all know income or feed cost is heavily related to the profitability and net return on the farm. So in this case, we can look at this number very carefully and how that changed according to our changes in strategies that will try to decrease greenhouse gas and nutrient balances. And you can see here the difference of income or feed costs in lactating and dry cows. Only dry cows obviously is negative, and what's the feed cost per kilogram of milk in this case. The DairyPrint has a report system that it's very nice. That they will spend quite some time developing that, so it looks really nice. You can actually click there and download a file that will report all the input that were entered and the situation in the actual situation, and what's the footprint that we expect with that. And here are only a few examples of what we can do with that. And then after we see and discuss these examples, hopefully we can go and actually see live the tool. So this is a herd of 150 mature Holsteins, adult Holsteins. They weigh 1,500 pounds when they are adult, mature. That, as I said before, help us to have the growing curves and the curves that change across the lactation. And this farm is located in Dane County, Wisconsin. It has a calving interval of about 15 months, so that gives us an idea how fast they are reproducing. So it's somehow accounting by the rate of reproduction or pregnancy rate. We decided to do that in order to make it easier. It has this herd 35% of cooling rate and 24 months on average at first calving. Production is 40 kilos, doing 3 milkings, and the bedding is chopped straw using slurry manure, and there is a crust formation that's done on the farm, and the lagoon or the pond is emptied only once a year during fall. Okay, so that's the baseline, the number one here. In that case, our estimate of methane was 54.7 tons per year, and most of it came from the herds, 52%, and almost all the rest from the manure storage. Now, if we do only a change, and we change the bedding from straw to sand, we see a substantial decrease in the methane emission. In this case, is about 7 from 47, from 54 to 47, so like 7 tons per year less methane being emitted by changing from straw to sand. So that's quite significant. Actually, I mean, between 10 and 15% of decrease by doing so. The distribution of from where it comes, herd and manure storage doesn't change that much in this case, but the amount, the total amount decrease substantially, which is important. What happens if we actually introduce a biodigester, and we know that has obviously capital investment on top of that. But if that would be a possibility, our emission will decrease even much higher, right? So 39, so it's almost 15 tons less out of 54. So we're talking about here 30% of decrease of methane emission by putting a biodigester on the farm. And when we do that, actually you can see now our proportion of herd methane emission will increase proportionally because now we will be taking care of more of the manure storage part of the emissions by putting the biodigester. And how about if we, instead of emptying the manure storage only once, that you see here was only in fall, and we empty twice, so spring and fall twice. So in this specific situation, that's the highest decrease in methane emission to 37 tons per year. You see, that's interesting from our standpoint of view, because this probably doesn't require the highest investment. This is a low-hanging fruit that farmers, if they are not doing, they potentially could do it very easily, simply, and it will have actually the best return on investment regarding environmental decrease of the footprint in this case. But in order to get this, we need a tool that will tell us, and we are very confident on the results because we have the solid background behind it. And obviously, when we do that, last point I'm kind of making this slide is we are decreasing most of the manure storage emissions. The herd will increase in proportion because we haven't actually attempted to still yet here to decrease that because the enteric methane being produced for the cows will probably remain at the same level as before. The same herd with the same characteristics, and here showing the ammonia emissions for different scenarios. This is the baseline as before, producing 5.4 tons per year of ammonia. And in the two other diagrams here showing if it is the pond emptied twice a year, you can see here the decrease in ammonia. It's very small. Even we can disregard that change and we can say there hasn't been a change in ammonia. We know from the previous slide that the methane emission will decrease quite a bit, but not the ammonia emission. But if we put a biodigester, actually, we not only not decrease the ammonia, but we will have higher ammonia emission. So we are aware that sometimes when this strategic management, we decrease some component, in this case methane, for example, putting a biodigester, but we also need to be conscious that other components like ammonia in this case will increase in amount. So something to keep in mind as we do these strategic decisions. This is some graph from a recent paper we submitted with Tadeo. And here, the only difference, the herd is different size, but all the components are very similar to the previous scenarios. Okay. At the end, the report here is kilos per kilos of energy and protein corrected milk. So really, the herd size, it's only for the analysis internally, but the results here are made by actually energy corrected milk, energy and protein corrected milk. So this is very interesting in our mind because this includes a lot of different potential management strategies and the methane intensity emissions in CO2 equivalents per kilo of corrected milk. Okay, so the first thing is here we use 3-NOP. So that's distinguished by the different colors on the bars. The clear ones is when the 3-NOP is being used. And here we use a standard dosage of 70 milligrams of NOP, 3-NOP. And that, according to the literature, decrease emissions of about 23.5%. That could change. There is still a lot of research going on this area about the dosage and the amount of decrease, but I think that's a good number to use as a good reference. So you can see for sure all the clear bars are lower than the darker bars. So using 3-NOP will decrease emissions. That's for sure. So that's an important fact that you will see here, right? Indeed, if we see on this top left corner block, this is the lowest emission block. And actually the very lowest one is when we use 3-NOP and we use sand as bed. We have a biodigester, we have a solid separator, and we have 24% of NDF and 19.5% of ADF in the diet. So the minimum is 0.644 CO2 equivalent per kilo of energy and protein corrected milk. Now we can see in the other blocks how these changes are different specific changes or strategies on the farm, right? So the others will be higher than this one. So this will be the optimal situation, starting with that. But in these other cases, for example, if the NDF is higher and the ADF is higher as well, we can see what's the numerical impact on increasing the levels of NDF and ADF on the diet. What happened if instead of biodigester and solid separator, we have a pond? And in addition to pond, we have the higher levels of NDF and ADF. We can see a much higher emissions. And if we don't use 3-NOP, we will be very close to the one that we said is like the benchmark we were looking at the beginning, right? Indeed, the highest level of emissions will happen on the other extreme here, on the bottom corner here, when we use sawdust as bed. We have pond for the manure management and high NDF and high ADF. And obviously, we don't use 3-NOP. We go above the threshold of 1 CO2 equivalent per kilo of energy and protein corrected milk. Okay. So we are very confident that this model, the DairyPrint, can help farmers to plan, to strategize what they can do to improve their environmental standing. So we try to do as user-friendly as possible, as intuitive as possible, and try to respond what-if questions. As I mentioned at the beginning, this has been, I just want to acknowledge, has been funded by the Dairy Innovation Hub in Wisconsin. And it has been a very fast pace. It's what they call, they have this grant they call high impact short-term grants. So everything has been developed actually. The whole model and the application has been, I think, developed in a period of time of about 8 months, which is also good to mention here as part of the whole process of making a very user-friendly and very minimalistic and as simple as possible model. I think it's also important to make it in a short period of time to respond to questions that are very, very important. So this is the prompt for me to move to the website. So I'm gonna switch now to a website. So I'm gonna stop sharing here. And hopefully be able to share my website here. Okay, I trust you can see now a web browser, and if I can point here, I mean, everything starts, if you just write dairymgt.info, it will be redirected to the website and on campus, but that's, or if you Google it, you will be easy to find this place. And here you will have a section of tools. Actually, in the tools, you will have a long list of different management areas, as I mentioned before. Feel free to visit and explore as much as you can. So, but today we're going to go to the environmental side here, and then we have the DairyPrint, and there is a number of additional materials that you may want to watch and look at. And there are some press releases and some other papers, abstracts, posters from the ADSA last year. But here is the link to the actual tool. So I'm gonna click on it and it opens. And before I do anything else, I wanna actually, we almost instinctively we just click OK here, but I think it's important to read what it says here. So to run the model, you first need to calibrate. So you see here, right there, there is a run thing. So that needs to be clicked. Otherwise, nothing will be calculated behind. So that needs to be done. But all the other tabs will respond immediately. You don't need to run anything afterwards. So you run only one time to calibrate the herd part of the model. So I will click just OK here. And we are into the tool, actually. And so here, we can define a herd. We can expand and collapse the different cards. I think that's the word that Tadeo uses for this. So we have a different cards. Each one pertains to a different type of information system. So for example, we can change the number of cows if it is a larger herd of 1,000 cows. Every time I'm changing the number, I will just keep it 150. It tells me here that I need to run. If I change any number here, in order to see the results, we need to run. So for a moment, let's assume this is a farm. Let's leave the default farm here that we are working with, that has this calf feed management and milk composition levels, that has this diet information. It's a standard farm, let's say, but let's do a change here. For example, let's do a nutritional strategy to mitigation. Let's use NOP, for example. 3 NOP and the dose 70 milligrams, for example. Let's assume we can do that. Hopefully, sometime soon that will be available here in the US. So, and then one thing important not to forget is we need to click here, run. And you see when it runs, it gives us what's the proportion of animals we will have in different situations, and what's actually the stability of the herd, how many we are producing, and how many replacements we need to keep. What are the performance metrics? As I mentioned before, the manure excretion, and you can see here actually manure excretion as well by months in lactation, by different groups of animals, primiparous, second lactation, multiparous, and what's the nutrient excretion as well. Actually, in the previous one, we had also here in this format by months in lactation the methane emission by different groups of lactating cows as well. Same thing with the nutrient excretion, which is very important. In the next part, we have the manure handling. I do think, and I want to call your attention to this manure handling and management on the top here. We try to keep this as simple as possible, but this is very important indeed in this system. I mean, now we know very clearly there are two very important components of methane emission. One is the enteric methane. We do have some possibilities to change, right? But probably the highest low-hanging fruit to change at the moment is here in the manure handling. We can do stuff available to decrease methane emission, in my opinion, easily on this part now. Once we get more additives and more research on that area, enteric methane could be an important part of the solution as well. So here we have the manure and greenhouse gas emissions. Here's the methane in these graphs. We have the ammonia as we saw before, and we also have the weather data available here. One thing we didn't see in the PowerPoint is actually the purchase feeds and crops raised in the farm, right? So here actually in this section, the user, this is the best way we came up with this, because as I mentioned, we try to be as simple as possible, but there is no other way around, because the user needs to enter what are the feeds being purchased and imported to the farm, right? Like, for example, if they bought corn grain, how much it was, soybean meal, etc., etc. And the same thing for the homegrown crops. The user can select here how many crops have been grown, and for each one, it will be able to define what has been the area, the yield, the manure that has been used on that crop, etc., etc. I'm going to go back to 2 because I don't want to screw anything in the system. If we do a change here, we need to be careful that we actually put actual data. As you see here, for example, in this case, we have 2 crops and 80% of the manure is being going to this crop and 20% to this crop. If we have more crops, we need to make sure we split the manure being produced on all these different crops in a consistent way. Very good. And the last part before going to the dashboard is the miscellaneous. So here is very simple to define just what are the costs and the prices, mostly for feed and for milk. And fuel consumption could also be defined here. That's part of the whole analysis as well. And finally, the dashboard here that gives you what is the carbon equivalent per kilo of milk, the intensity of methane, and the different components as I discussed in the PowerPoint. And in the bottom, we will see for nitrogen, phosphorus, and potassium, the balance of these nutrients on the farm. And I think with that, it would be a good moment to stop myself and hopefully entertain some questions or discussion if there are any.